Okay. All right, we're back again. Wow. Yes, right. So this is now Bob, Big Orange Bramble from University of Tennessee, EECS department. My name is Mark Dean, and I'm here to introduce the application demonstration section of our particular project, our 64-node Raspberry Pi based supercomputer. So first up is Parker, going to talk about HPL, right? Okay, cool.
All right, so I'm Parker Mitchell, senior in computer engineering, and I'm going to start by talking about some benchmark results. So we used HPL, High Performance LinPack, as one of our benchmarks to evaluate the performance of our machine. HPL is an industry standard benchmark commonly used for supercomputers. So if you've ever seen the top 500 list of supercomputers, they base it off the numbers coming out of this. It was created here at the University of Tennessee at the Innovative Computing Laboratory, Dr. Jack Dongara and his team, so we might be biased towards it. So it solves a dense linear algebra system, which is a highly parallel process. So your typical AX equals B type system. As a part of that, it requires a linear algebra library. And so this is where you're allowed to do some of the optimization for your machine. In our case, we looked at a couple options, Atlas and OpenBLAS primarily. Atlas did not give us properly optimized code. My hypothesis is it doesn't get properly vectorized and optimized on the ARMv7 ISA. There's a lot of strange things that occur, but the performance was an order of magnitude better with OpenBLAS. So we went with OpenBLAS, which has hand-tooled instructions, and it seems to give pretty close to optimal performance on a single node, which tells us that it's probably a good choice. So here's the algorithm in a very brief overview. So it solves AX equals B using LU decomposition, or you may also see it called LU factorization. So the process of actually decomposing it into a lower triangular matrix and upper triangular matrix breaks it all down, and then you can use those to solve the actual system. The matrix, they say, is of order n, which is a parameter you specify, and then it's divided into blocks or submatrices of size nb, and then you have a process grid of p by q. So in the figure, you can kind of see this color-coded arrangement of squares, and basically, if on the left this is your A matrix, so your coefficient matrix, it's going to do this cyclic distribution, and then it's going to map it to the right to your process grid. So P would represent your rows, and Q represents your columns. And so it will divide your starting matrix on the left into a process grid as what you see on the right. So the HPL parameters are another place where you can optimize in addition to your linear algebra library. We settled on doing our matrix size of roughly 10,500 squared times your number of nodes and the square root of that. The reasoning behind this is if you look at the memory utilization on a single node, you can maximally hit about 10,500 as your order of matrix, or your size of your matrix, and fit into RAM and not incur any swapping penalties or run out of RAM. So you want to try to maximize, in most cases, your matrix size for performance reasons, but you want it to all fit into your RAM. Block size, I settled on a size of 100. But there's interesting performance implications from your block size, and it's sometimes difficult to figure out what's actually optimal. So 100 could not, it could possibly not be the best block size for our system. It was determined basically by doing a parameter sweep and going through the possible options. Your block size both affects your performance on a single node and your performance distributed across a lot of nodes. So on a single node, it affects how it divides things up and gets processed, but on a distributed system, it also affects your communication. So you have to take both into account. And so you can't just do the fastest single node, potentially. You might also have to balance its effects on your communication. The broadcast algorithm is a bandwidth reducing variant. I think they call it long is the algorithm. I'm not sure why it's called that. They abbreviate LNG if you look at the actual parameter file. A process grid of P by Q. We tried to aim for mostly square. There is a constraint where Q must be greater than or equal to P for reasons I won't get into. And so we try to make it mostly square, and that's when you get the best results. Setting a P of 8 and a Q of 8 actually maps nicely to the topology of our computer because Q represents your process column. And so you can think of having 8 columns and 8 rows as representing our 8 towers of 8 nodes. So it seems to map well to how we've set up our networking. And then another interesting thing is the look-ahead depth. So this has some implications for the communication as well. We went with a depth of 0. If you look at the HPL website, you'll see them recommend a depth of 1 or 2 typically for the best performance. But enabling it seemed to cause a performance regression. I don't know if I have a great explanation for why that's the case. It could be because of our slow interconnect, and so the overhead of trying to add that additional communication. It could also be due to our small amount of RAM. So we would potentially have to reduce our problem size to enable look-ahead depth because that requires more RAM to utilize that function. So a few different theories, but I'm not really sure why that's the case. So to elaborate more on the broadcast algorithm, there's these 2 graphics from the HPL website. The one on the left is considered the scatter phase. So if you see this, this first collection of squares, this is referred to as process 0 in this example. And process 0 is the node which wants to send out the broadcast message. So it's wanting to communicate. So it'll start by scattering across all the nodes in its process column. So it's going to divide the message into Q-1 pieces, and it's going to scatter them in this type of fashion across the nodes. Once it's completed this, it will then do what it calls rolling the message. And it's going to have, if you think of this as being a group of nodes that kind of just wraps around, it only exchanges with its nearest neighbor to the left and to the right. So process 0, in this case, will trade messages with process 7 and process 1. And they basically just pass messages back and forth until you get to the final picture of everyone being synchronized. The interesting thing about this broadcast algorithm versus the typical broadcast algorithms that are used is this causes all the processes to stop and synchronize. And typically this algorithm would be slower on most distributed machines than using one of the ring variants. However, this algorithm is considered to be fairly competitive and potentially better when your nodes are much faster than your network. And the Raspberry Pis are not particularly fast, but our network is quite slow. So the trade-offs of doing it this way actually seem to pay off. So the results, the important part. So I've calculated the theoretical R peak to be on the order of 440 gigaflops. That's making the assumption of being able to do a scalar multiplication every other cycle, while simultaneously being able to do a scalar addition every cycle, and estimating that to be 1.5 flops per cycle. So our actual R max, so our best performance on HPL, was achieved at our full 64 nodes. It was just under 150 gigaflops, which is not bad. It's on par with, say, a decently high-end workstation. So it's not considered a supercomputer today, really, but it is pretty good performance. Our scaling efficiency was approximately 37% if you take our single node performance and extrapolate that up to 64 nodes. We're only achieving 37% of what that should be if it was linear. It's likely due to our interconnect. 100 megabit Ethernet is a severe bottleneck. If these had gigabit Ethernet, I would expect that number to be maybe even double. So if you look at some historical results, June of 1994, we would be the fastest supercomputer in the world, and we would be top 500 in the world for June of 2002. So that has been some time ago, but this is performance that is, of somewhat significant. And here's a graph of our results. So it looks fairly linear just glancing at it, but it does slowly taper off in scaling efficiency. It tapers off the most right here in the initial part. So you go from single node to two node performance, and your scaling efficiency is already dropping to 70% or less. And so it very quickly tapers off. And then it is mostly linear from that point onward, where your scaling efficiency very slowly tapers off. The next benchmark that I'd like to discuss is HPCG, which is a newer benchmark, whereas HPL is probably older than I am. HPCG is a new benchmark to address the shortcomings of simply looking at HPL. It's trying to be more realistic performance, and it's trying to provide a lower bound. So the terminology that you'll hear from the ICL is it's trying to be the bookends of performance. So it's going to fall somewhere between HPCG and HPL in a realistic application. It also solves AX equals B. However, it's doing it on a sparse matrix representation, and it's using a conjugate gradient method, which is something that you can iteratively do on a sparse matrix, whereas HPL was using LU decomposition on a dense matrix. So sparse matrices are important for when you have really big problems. Sometimes you can map it into a sparse matrix. Maybe you wouldn't otherwise be able to represent it, is one example. And so Bob achieves just over 5 gigaflops per second on just the pure reference implementation. This number may sound low, but to put it into perspective, the same workstation that I used as a comparison point that showed higher HPL performance than Bob was able to achieve less than a gigaflop on HPCG. So this is fairly meaningful performance, and it's not a terrible number for the reference implementation. considering our architecture. I won't go into a lot of detail about the actual algorithm. It's mostly over my head, and it would take a long time to explain. But here's the diagram that they show in their handout. One interesting thing to note is they map the data a little bit differently. They use this notion of a 3D grid instead of a process grid, P by Q. And our results are incredibly linear. At the very top, so 64 nodes, we're achieving on the order of 94 to 95% scaling efficiency. So I'm very happy with those numbers. Now I'll hand it off to Sean.
Hi, my name is Sean, and the next two applications that you'll see are actually demonstrations that were provided with the original Tiny Titan reference that was built for the original Raspberry Pi 1s. The first one is SPH, the Smooth Particle Hydrodynamic Simulator. What this simulation is going to do is it will have one node that handles dividing the task up amongst the worker nodes and handling the rendering of the fluid dynamics simulator to a screen that anyone who is passing by can see and interact with using keyboard, mouse, Xbox controller. The worker nodes handle calculating the interactions between neighbors for whether or not the particles are attracted, repelled from each other, and so on and so forth. And because it is a live demonstration, I can start it running. One important thing to note with these two applications is that they are an oddity when compared to the others. Most applications are required, or they distribute the work across a collection of worker nodes. Those worker nodes do whatever calculation they're required and report back their findings in some way, whether it be in a text file that has all the data collected in it, or if it's just reporting back to further a later calculation. These two applications report back to a node that has to be hooked up to the periphery device. It has to have the monitor to display. It has to have the keyboard and the controller for input. So we had to work around our job manager, our Slurm implementation, in order to find a way that we could actually get the applications to run on not only the 64 worker nodes in the Bob cluster, but also on the head node, which was connected to the display and input devices. So, of course it stops. Okay, so, no, it just stopped entirely. One minute.
It always happens.
Always happens.
It never fails. I've been surprised.
Okay, here we go.
Recovery.
Can you tell I've done that a couple times?
Yeah.
Okay, so as you can see, the user using the Xbox controller is allowed to move a ball, change the size of it, and configure various parameters of the system, like reducing gravity, increasing the elasticity between nodes, and increasing the atmospheric pressure in the simulation. If we switch it to the per node display, you can see the way the worker node or the master node is dividing the work up between each of the worker nodes. And then we can actually decrease the amount of nodes that are being used in the simulation. So a single node holds all of the work here. For the purposes of having a clean display, the particle count has been kept down. The physics of the simulation actually goes a little wonky when we increase the particle count to decrease the frame rate.
Wonky is a technical term?
Well,
As technical as we
the water particles start bouncing off of the water when no perturbation is applied to the
Oh,
system.
now that sounds technical.
I prefer wonky.
Okay. It's fair.
So you can see as we scale more nodes in that the master node is able to reassign the work across the other nodes.
How many nodes can you reassign?
You can run it as many nodes as you want. It scales fairly well. It has a way of generating unique colors for each of the nodes. However, given that even at one node it is able to hold a solid 60 frames at this particle count, it's hard to demonstrate any real scaling besides distributing it up across more nodes. So that is the SPH.
So the
simulator.
network doesn't get in the way when you.
The network does not get in the way in this problem. However, it does in the next. Okay. So if I come over here, I can launch Pybot. Pybot is a Mandelbrot race simulator where what it does is for any given complex number, you can determine whether or not it is a member of a Mandelbrot set. Given a two-dimensional area, you can think of each of the pixels corresponding to a complex number. You can check each of those pixels to see if its corresponding complex number is part of the Mandelbrot set, and then shade a region based on membership in the Mandelbrot set or not. So what Pybot does is it will take one worker node and put it on the left side of the screen and tell it to test the Mandelbrot membership of a given region. It takes the remaining n-2 nodes, puts it on the right, and then has all of those worker nodes perform the exact same calculation in parallel to demonstrate the relative speed up that you get when you divide a process up across multiple worker nodes. So if I run Pybot with its default settings right now, it will allocate 16 nodes that will start the Mandelbrot race. As you can see, the collection on the right is moving significantly faster, approximately 14 times faster than the one on the left. The artifact of the line appearing is just a rendering bug where the file is being used, it's being rendered on both sides, but I'm not entirely certain why that is, but it is the n-2 nodes over here. It's the node that's being rendered over there. It's getting skipped over in the calculation, and it has to go back and fix it because it didn't actually get the task from a previous MPI task. So you see now that the one on the right is finished, the tasks are switching over to the left side.
And this is 16 nodes.
This is with 16 nodes.
16 nodes.
One thing to note is that the network actually is a limiting factor here. So what you're seeing is the relative speed that the MPI commands are being able to report back to the master node. When I tell this to run with, say, 64 nodes, our entire cluster, provided it doesn't break on me again. Does anyone have anything running right now? It says waiting for resources.
I do. I'm using 8 nodes.
Oh. Okay.
Try 56 then.
You can kill it if you need to. That's
The scarcity of resources is like gotta run during the presentation. Gotta sneak in for months.
There. There's 32 nodes. Okay, so hypothetically, this should be running twice as fast as the first one. And you see that the one on the right is still moving significantly faster, but the single task on the left is moving significantly slower than it was before. That's because the network traffic is being flooded by all of the MPI tasks being completed on the right, and the one on the left is not actually being able to render appropriately.
Your line also is more is at a higher point.
Right, it's at the higher point because the task that isn't being assigned, because it's only running n minus one of the workers on this side, it ends up higher on the queue when it has to go back and re-render it.
So it's not running twice as fast as the previous. How much faster is it running? 32 versus 16. Do you have an idea? Is it 50% better?
Because even at low numbers, the Raspberry Pi 3s are significantly faster than the original Raspberry Pis that Tiny Titan used. The entire simulation up to the point where the left side finishes is approximately the same time regardless of how many nodes are being used. Give or take a few seconds, but that's just noise.
Okay.
The image on the right will complete in approximately twice as fast. Okay, and that is PyBrot.
Cool. Thank you.
I'll turn it over to Kelly for numeric integration.
All right, I'm Kelly Duso. I did I'm a master's candidate in computer science. I did the numeric integration application, which, similar to Sean's application, was adapted from the Tiny Titan repository. I'm assuming this was something that they probably used to kind of test MPI because it's very straightforward. So just as a refresher, integration is just finding the area under a curve. A really simple way to do that is to use Riemann sums. There's 3 different types of Riemann sums. Depending on which type you use depends on you get different results depending on which type you use. So for this example, we have f of x equals x. So you can see that the left type of sum is going to give you kind of a lower estimate than what you're looking for. The right type is going to give you an overestimate of what you're looking for, and the middle sum is going to kind of give you somewhere in between. However, the application that I wrote is using the right sums, and we can adapt it using the other 2 types if we want to. Should be fairly easy, but I figured it was somewhat unnecessary to do because it's kind of a proof of concept. So the way this application works is it takes 3 different user parameters. So you're going to get your function. So in this case, before we use f of x equals x, you're going to get a domain. So if you want to do your area from 0 to 5, you're going to input from 0 to 5. Your number of samples, which is kind of weird because this is however many cores you have, this is samples per core. So if you want to do a really exact estimation, you're going to want to use a larger number of samples because that's going to be based on cores, not your total number of cores. The next thing that the program does is it gets the number of available cores. This is not something you specify. It just looks to see what's available and then takes that and uses it. And this is where the parallelization starts. The width of each rectangle is then calculated, and then the domain start endpoints are calculated to do all of the samples within that chunk. The areas are then all calculated, and MPI will then sum and reduce in a function that it has all of the area values that are calculated. And then the last thing we do is calculate error based on the SciPy integrate definite integral, so then we can figure out what our error actually is. This is a really small example of what the program does. So here we have cosine as our function. And this is the actual place where the user will input their information. So we're using cosine here. Our domain start and end is from 0 to pi, which we should be getting 0 as our results, right? The number of samples that we're using is 10. So if we had 8 cores that we were using, it's going to give us 80 rectangles worth of area total. And you probably can't see it because it's super duper tiny. But on this example, we used 128 cores. Our actual area that was calculated by the SciPy function is 0, which is correct. The Riemann area that we calculated is 0.00245, so obviously we're going to have an error of negative 0.00245. And the time that this took to run, so it's fairly simple, is 0.283 seconds. Fairly quick. That's it.
All right, I wrote a really simple program to calculate pi in parallel. Several reasons. One, it was just to demonstrate Bob's ability to efficiently scale embarrassingly parallel tasks, which are tasks that can be easily divided up into subtasks of approximately equal size, and that require little or no inter-process communication between the worker nodes. It was also important just discovering remaining issues with MPI for pi or Slurm, and then also just seemed appropriate to calculate pi on a bunch of Raspberry Pis. So the way it works is you take, so an infinite series can be used to approximate the value of pi. So you just take the first n terms of the infinite series, and that'll give you a good approximation. The great thing about that is that then you can easily divide up the summations into smaller summations that each of the worker nodes can do in parallel, and then they can pass back their partial sums to the head node to do a single sum of the results and provide us with an approximation. So the first one I was looking at was the Leibniz formula. This one is very simple to implement, and it's been done by, I'm sure, plenty of undergrads. I'm sure a lot of you all have seen it. The issue with it is that it converges extremely slowly. After about 5 billion iterations, you get pi approximated to about 10 digits. So then I tried BBP, which after only a few thousand iterations can give me close to 1,000 digits of pi. The way I implemented it was using a Slurm batch script to handle my Python script. Python itself is using the BBP formula. The head node simply distributes to each worker node which portion of the summation they'll be adding up for their partial sum, and then it gathers all the results, adds them together, and spits out the answer. And so as far as scaling results, and I want to point out this is on a logarithmic scale, so we're starting off here with a single worker node running 4 processes all the way up to 64 worker nodes running a total of 256 independent processes. And with each doubling of the number of worker nodes, we're seeing almost cutting in half of the runtime. Not entirely, and that's for a good reason, which I'll get to in 1 second here. So the reason that you usually cannot expect to see, as you'll see, like I said, you'll see a diminishing return value as you add more cores, and that's because of Amdahl's law, which basically says that one way to say it is that your speed up is going to be related to how much of the program itself can be parallelized, or another way of saying it is that you're going to be bottlenecked by the portion of your program that cannot be parallelized. So the way this works is that S, your speed up there, is equal to P is the percentage of the process that can be parallelized, and then N is the number of processes that can that are being run in parallel. And so I did a rough guesstimate that approximately 99.871% of the program is able to be run in parallel. There is still some small work that has to be done by the head node alone. The gathering of the data, the receiving back the summation, and the printing of the results. And so if we look at S, for example, on 256 processes from 64 nodes, that would give us a speed up factor of about 193. Whereas for a single worker node running 4 processes, it was about 3.98. So basically what it's saying is that you're going to see really good scaling numbers at first, but you are going to hit that plateau after 32 to 64 nodes, where adding more nodes is not going to pay off at all. In fact, if we were to double the entire size of Bob and go up to 512 nodes, I believe at that point the speed up is expected to be around 308. So just something to keep in mind for incredibly simplistic, easily distributable tasks. There's a point at which throwing more nodes at the problem is not the answer to speeding it up. So that's it.
Cool.
So Greg and I have both worked on the Monte Carlo simulation application, and this was one that was requested by a faculty member with certain specific things that needed to be inputted and certain things that the program needed to do. So quickly, Monte Carlo simulations utilize random sampling to create output for the user. The example that we used over and over for this was rolling a dice because it's really simple. You just get a number back, you make sure that you get a number 1 through 6, and then you check that. The driver program is called mcbatch.py. This is really kind of the foundation of the Monte Carlo program because it actually takes all of the info from the user and creates the output. And then there's a GUI that Greg created called mcgui.py that you can use to also input stuff. There's 4 different parameters, I believe. There's a required 3 parameters. We'll go over those. So there's 3 required parameters, but there's other ones as well. Currently, it's only allowing C, C++, and Python to run. I know Octave was something else that we wanted to include, but Octave, as far as I know, currently is not installed on Bob. So as soon as that is installed, we can include Octave files as well and test those. So the user parameters that are required are the input executable file path, which we recommend using an absolute path, the output file name, so whatever you want to call your output file, and number of runs. These are required. I think we might end up changing number of runs to be optional, but you have to include either number of runs, maximum runtime, or a deadline, just so your program doesn't run forever and ever. The optional arguments are maximum runtime, so if you wanted to run for, say, 2 hours and then kind of see what your output looks like, you can do that. A deadline, if you want to say, I want to set my program to run until 2 o'clock on Sunday, that's an option as well. And you can also specify the number of CPUs. So if you don't want to utilize all of Bob and you just want to use, say, 8 nodes, you can specify that so you're not taking up, the whole thing. Simply, a batch file is created and it's submitted to Slurm, and then whenever the number of nodes becomes available, it will run and give you output. And a quick example file that is produced by our application. So we have, in this particular example, we have 8 nodes that are being occupied. Our job name is Monte Carlo dice roll, so this is just another dice roll. Our output's d.text. We do have it specified now where we have an error file that is created just in case your program creates some kind of errors. You do have a way to go back and check and see what's happening with that. And this is running 100 different dice rolls, but it's split up, as you can see, into different chunks. And this is based on what the number of nodes is that you're using. So kind of the remainder that you have is going to be the first portion that's run, and then you're going to run 4 times, so 4 cores, based on the number of nodes that you have up there as well. So this will end up giving you 100 total runs. Right. And FDS will be Caleb.
I'm Caleb Williamson. I'm a master's candidate in computer engineering. I'm going to talk about Fire Dynamic Simulator, FDS. FDS is a large eddy simulation. It's used to model fires in rooms, structures, large buildings. It also is used to do heat transfer and smoke from fires. We ran into a problem immediately in that the Fire Dynamic Simulator is designed for 64-bit systems now. So we had to go back and dig through their documentation to find a 32-bit version. So that was a fun challenge. But it did work. And so we were able to take advantage of the parallel processing of Bob by dividing up rooms into a series of meshes. So each mesh interacts only with the meshes that are around it, and it takes into account things like heat transfer and airflow and other things that would matter in the case of a fire, including smoke. It's best if one mesh is assigned to one processor or one core inside of Bob, but you can actually do multiple meshes for one core. Our work was actually based on the work of Donald Collins, who was a master's student for Dr. Icope here at the University of Tennessee. And his work actually shows here with a sample room fire that is a couch actually on fire. And you can see that after 4 meshes here, it kind of flatlines in performance, and it actually goes up a little bit once you get to 32 and 64 meshes. So the way that FDS works is the way it divides the information. Eventually, the overhead of communication is going to outweigh the performance benefit of adding more cores. So it's important to note that at about 16, we stop gaining benefits and we start seeing a loss in performance. And this actually proved to be true on our own cluster here. At around 16 was when we saw a flat line, and at 32 we started to go back up again. So Bob actually performed pretty well compared to a traditional compute environment. So I was pretty happy with the results, and I think FDS went really well for Bob.
So is that 16 nodes or 16
Or,
cores?
sorry, 16 meshes with 16 cores.
With 16 cores.
Yeah.
So it's really just
4 nodes.
nodes.
Yeah.
So now I'm going to talk about DANA, which is a neuromorphic architecture. DANA stands for Dynamic Adaptive Neural Network Arrays. We used Bob to generate networks for DANA. And so DANA consists of a configurable grid of elements. So these can be neurons or synapses. And there are varying parameters for your neurons and synapses. There's a fast software-based simulator available in addition to the FPGA implementation. So because of this simulator, we're able to run this on something low power like a Raspberry Pi because the simulator is fast enough to still run reasonably well. These networks are generated through a process called evolutionary optimization. So the idea is you can't just intuitively generate a network for a complicated problem through hand tooling, and our approach does not lend itself well to other commonly used systems for other neural networks like backpropagation. We were able to generate a network that solves the pole balancing problem, which is the inverted pendulum problem, in just over 3 minutes, which can survive for 5 minutes of simulation. We used 5 minutes of simulation as kind of a benchmark of how long it takes to get to that point because it's something that is able to sufficiently show scaling results. So just to elaborate a little bit more on the structure of DANA, this is a visualization of what DANA actually is. This is showing a 10 by 10 network. So DANA specifies a grid of potential elements, and you can use as many or as few of these elements as you want and configure them however you would like. So there's a very large problem space that you have to explore is a key point. So the pole balancer network specifically uses input neurons for 4 different types of inputs. So there's input neurons which will accept the pole position, pole velocity, cart position, and cart velocity. And based off of these 4 parameters, it has 2 output synapses, and they output either push left or push right. If it wants to push left and right, that'll just cancel out, and if it does neither, then it also is effectively the same. So there's a short little video to demonstrate this is what it's actually doing. So this is the network activity on the right, and on the left is the pole balance visualization. Bob was internally running the simulation behind this to determine the fitness of a network as it performed the evolutionary optimization. So this is just a visualization of what it was doing in the background. So here are the results for the evolutionary optimization. So there are 2 different evolutionary optimization programs which I used to test. I used the local evolutionary optimization code, which uses a larger population size and does not use MPI It does everything just on a single node. And so that's how I came up with the kind of the baseline result of one node. And that's why I specified none for the distribution algorithm. And then I used a distributed EO program for all of the other tests. This distributed EO program has been run on Titan, the supercomputer at Oak Ridge. So it has been tested pretty well. There is, I believe, a pending research paper on that, which will get cited in our final report. So looking at the table, and I'll put up a graph in just a moment, you can see just from the numbers, it quickly levels off. So your scaling factor continues to increase up to 32 nodes, but potentially due to our network topology and the fact that there's two sets of 32 nodes which have their own switch and then a limited bandwidth in between, or potentially just due to the problem, the scaling severely tapers off after 32 nodes. So just a graph to visualize these results. It makes it even easier to see. So the scaling is actually quite good in general, moving from one node to anything other than one node. So I feel pretty good about the use of distributed EO on Bob. However, for the pole balancing network specifically, I would probably recommend using 16 or 32 nodes maximum, because otherwise you're not really gaining much. However, it's possible that on the generation process of other networks, it would have different or somewhat different performance metrics. Specifically, the pole balancing network has a very simple simulation. It's just very simple algebra. But if that simulation was something more complex, that could change the performance dynamics. So that'll be some further testing to look into.
So did you compare this to what you're seeing on the machine you're using the simulator on now? I mean,
Titan?
No, the other, you're just running it on a simple workstation.
Yeah, so if you compare it to the laptop from where the software team members, this outperformed his laptop. We actually did a side-by-side race. And this, I mean, Bob was complete before his laptop was through a third of the evolutionary optimization.
So Bob, at what, how many nodes?
That was at 16 nodes,
At 16.
which pretty much characterizes the performance. You gain very little by moving to 32 and much less by going to 64.
Okay.
But even at 8 nodes, it will outperform probably a lot of laptops for pole balancing, and by 16 it's definitely very competitive. I don't have the performance numbers from Titan yet, but I do look forward to seeing that comparison. Obviously Titan, just a single node of Titan is more powerful than Bob, but it could be interesting to see how the performance compares.
Yeah, the scaling factor will be interesting. See where
Yeah,
it
it'll be
starts
very
to taper
interesting to see where it tapers off on Titan, because they have a much more sophisticated networking topology.
off. Okay, thanks.
So now we're going to talk about TensorFlow, which is in the same line of AI, but a different approach.
Hey, my name is Lou. I'm here to talk about the distributed TensorFlow that's implemented on the Bob cluster. So basically what we are trying to do here using TensorFlow is to implement the famous deep neural network that we have been using for quite a while, not too long. Well, different from data structure, we actually do use the backpropagation to to train our network. So with that being said, the modern deep neural network actually uses large data set and large amount of computation, including a really complicated model, to push the boundaries of what's possible in perception and language understanding and so many other related areas. But there comes a price for such a great data representation and understanding, which is large data set and powerful models, which includes a really large amount of computation. Traditionally, what people have been doing is to use multiple clusters, or multiple machines in clusters, including GPUs, to do parallel computing, especially on the matrix computation. However, when it comes to like modern usage, for example, embedded system and mobile devices, this is not quite possible. What we are interested in using Bob is to use this embedded system cluster to realize or to implement deep learning, try to see what's happening on embedded system. Recently, there are not too many studies or researches on this yet, so that's what we're trying to find out. The reason why we choose TensorFlow regarding other platform implementing deep learning is because recently TensorFlow has already included distributed system, especially supporting embedded system, and which is developed by Google Brain team originally. So when it comes to distributed learning, we have two choices. One is distributed model, which is model parallelism. Another one is distributed data set, which is data parallelism. So the differences between these two parallelism is, one, for the distributed model, you actually put a whole model into different nodes, into different nodes in the cluster. So you have to. This happens because the model, one simple model, is too big to fit in one node or one computer, and the data parallelism is because your data set is too large to fit in one machine. What we've been trying to do here is we actually choose the data parallelism instead of the model parallelism, because with the Raspberry Pi, it actually it's powerful enough to fit one simple model in one node in the cluster. And here it shows how we train, or how the data flows through the graph. The upper is the synchronized data parallelism. The down one is the asynchronized data parallelism. So these are all based on the data parallelism instead of the model parallelism mechanism. So the difference between these two is, for the synchronized data parallelism, we update the model which is stored on the parameter server. We have to wait until all the worker node which actually do the computation to finish their job, and we average this update, and we then update this parameter server. For the asynchronized one, whoever finished its training and provides the update for the parameters, we just grab the data and update the parameter servers. And whenever the parameter server finishes update, it's going to update, or it's going to transfer the updated parameters back to all its worker nodes. So we believe this way is actually more flexible and faster than the synchronized way. And based on some existed experiments done by others, the synchronized data parallelism is not necessarily more outperform the asynchronized way. So that's why we choose this asynchronized data parallelism for current implementation. Next, I'm going to ask Chen Chen, another member in the team, to talk about the specific convolutional neural network or the deep learning network that we implemented on the cluster.
Hi, my name is Chen Li, and now convolutional neural network is quite popular deep learning model used in computer vision, which is my research area. So, and one of the most famous architecture of convolutional neural network is the net, which is shown in the bottom picture. So we can say the net contains several layers, including the input layer, the convolution layer, a sampling layer, another convolution layer, another sub-sampling layer, fully connect layer, and the output layer. And each layer has numerous parameters. So, the competition is very huge, and we so now researchers tend to increase the number of layers to make the architecture deeper and deeper. So the deeper architecture can help us to find the intricate data representation for which can help us to do better in for image application. And we tried to implement a convolutional neural network based on the net, and for recognize handwritten digits, and the data set we use is MINIST. It has 60,000 training images and 10,000 testing images, and each image has 28 by 28 pixels. So the computation is very huge. So and this is why we choose to run the model on cluster. So we got now we get some primary results, and so the running time for training the model with one epoch and 4 nodes is about 1 hour, and the testing accuracy is about 89%. So we can run the model on any number of nodes, but the scaling performance is now not quite satisfying yet. So we need to do more information about our results can be found in our document. And in the future work, we need to do more work to implement the model to achieve better performance. Thank you.
Is that it? All right, so question on TensorFlow. What do you think the issue was from a scaling standpoint?
So from our results shows the scaling performance is quite weird because
Weird.
yes,
Okay.
because intuitively when as the the number of nodes increases, the running time should decrease.
Decrease.
But
It doesn't.
yes,
Does the running time increase?
yes.
Kind of, yeah.
It increases. All right. So
We look into the clusters when it actually do the computation. When we use like 4 nodes, the computation like intensity is actually way more than we use 16 nodes per node per se.
I see.
So it's like when it runs on more nodes,
Okay.
each node actually do less computation.
Yes.
Each node does less.
But
one
they're
day.
all doing it.
They're all doing it.
Yeah.
So it's spread across, but it's,
Yeah,
they're
we
not working that
we're
hard.
actually suspect if that's caused by the communication overhead because it has to, the worker node has to update the parameter server node, and the parameter server node has to update back to the worker nodes. So there's like some
Okay.
yeah.
Okay. All right, team. Well, let's see. Before we stop, I wanted to make sure that I got. I know that the video must be hearing this voice, but nobody in front of it. So I'm gonna move the camera back and down a little bit so people can see the system. There's another video that shows the system in more detail, but for those of you that are looking at this video, that is the system. I'll bring the camera back up, and actually I'm going to pan around and make sure everybody is on the screen here, so everybody say hello and smile. Hopefully you can see everybody, this great team of ours. I'm going to zoom around because I see that there's a few that are back over there in the corner hiding a little bit, so hi team. So again, thanks everybody. Again, this is a disembodied voice talking to the screen, but that's all right. Thanks again. I think we'll have one more video on future opportunities with this machine.
A few
And
things to clarify from previous.
okay,
videos
yeah,
and
some
then,
updates and a little bit more information.
Future
So
work.
stay tuned for our next video. Thanks a lot. Bye bye. Let's see.